So let's get started with the part C of our assignment, which is our discussion on X-rays. So we will cover what exactly are X-rays, how do you generate them, what are their different types, how do you filter them, and like what are synchrotrons. So let's get started. So what are X-rays? So X-rays are electromagnetic waves, and and their wavelength are of order of 1 angstrom, which is like 1,000 times smaller than thousands of times smaller than the visible light waves. And so that means they have like 1,000 times more energy than X-rays. And they are heavily like obviously used in medical technology and stuff. And they were like accidentally discovered by Röntgen in 1895, and he was also awarded the very first Nobel Prize in physics for this. They are like since then, like X-rays have been like extremely significant in like various technologies. So X-rays are generated when when we strike accelerated electrons on a very heavy metal surface. So what is the significance of accelerated electron on heavy metal surface? Like I will come to that in a moment, but basically the most simplest design of X-ray tube like includes a hot negatively charged filament, which is a cathode, and like using thermal emission emits electrons. These electrons are then like accelerated using very high voltage, and then these electrons strike a positively charged target metal. And when they strike it, we obtain X-rays, a very high energy X-rays. The problem with this process essentially is that it is like a very inefficient. So most of the energy is like dissipated in the form of heat. So that could lead to melting of anode. So to overcome this issue, we use what's called rotating anode. So these anode because they rotate, what happens is when electrons strike a different a part of anode, since they are rotating, the anode gets some time to cool off, and and in the meantime the electrons strike different part of the anode. So the heat is uniformly distributed across the whole surface of anode and so on. So basically it overcomes the issue of melting. We can also use different cooling techniques like water cooling as well to cool off anode and make the process more efficient. To collimate X-rays and to focus them, we can use optics like ellipsoidal mirrors or hollow glass fibers. Some mirrors also have the alternating layers of tungsten or silicon to produce or collimated X-rays. So different types of X-rays. So we have two types of X-rays: white radiation and the characteristic radiation. So white radiations are produced when these high energy electrons get decelerated due to electrostatic interaction with target metal atoms. So like again due to like interaction with nucleus of target metal, the electrons could change their direction or their speed could decrease and so on. So and this change in and this acceleration would lead to production of X-rays. The spectrum obtained is broad and continuous. So as we can see here, like in the intensity versus wavelength diagram, this continuous part is white radiation, and it is produced using deceleration. It is produced due to deceleration of electrons. And these X-rays only depend on accelerating voltage and not on the nature of target metal. So for different metals, these they would be similar. And so this expression of Emax is EU. So when electrons are accelerated through voltage of U, its kinetic energy becomes EU. And if suppose by some chance we can reduce the kinetic energy of an electron to 0, the change in kinetic energy would become EU. So the maximum possible energy of the X-ray which could be generated is EU. Therefore, the corresponding minimum wavelength which could be generated is Hc by Emax, which becomes Hc by EU. So this is like the lambda minimum, and as we can see below lambda minimum, it is not possible to generate X-rays. So it only depends on the accelerating voltage. It becomes pretty clear. Now, from this diagram, we can also see that at high accelerating voltage, at some wavelengths, we obtain extremely high intensities. and these intensities are called characteristic radiations. So what exactly is characteristic radiation is that sometimes these high energy electrons, they remove the inner electrons of the target metals. So what happens is the higher energy from higher energy shells, these shells, the electrons like occupy the vacancy and so on, and hence the X-rays are generated. And these resulting X-rays give sharp peaks in spectrum. These peaks depend on the nature of target metal. Why is that? Because as we can see, the lambda characteristic is Hc by delta E. So, and this delta E is the energy level difference for like atom. And we know like from the expression, like the difference in energy levels like increases with increase in atomic number. So if we use a different metal, the lambda characteristic could decrease or increase depending on its atomic number. Also, one more thing is that this is also why we use heavy target metals for like generation of X-rays. Because if we use something like sodium, the X-ray generated would not be like powerful, have energy high enough to be considered X-rays. They would be like ultraviolet or visible light. So that's why to generate X-rays we need heavier like metal, like copper, molybdenum, or tungsten, or something like that. So what's the effect of atomic number? So again, like I have discussed, as atomic number increases, the energy of the X-ray produced also increases. Hence, we can choose depending on like our needs. We can choose different target metal. So, for instance, if we are doing some if we need X-rays for medical purposes, like very high energy X-rays are required for that purpose. So, we use tungsten K alpha like X-rays for that. Similarly, if we are doing X-ray crystallography, we can use copper and molybdenum and so on. Absorption of X-rays. So, first of all, why do we need to absorb X-rays? Is because for different wavelengths, the diffraction pattern which we can obtain from X-ray crystallography could be like different. And yeah, so what happens is, suppose if we use K alpha and K beta emissions, both of them at the same time, the diffraction pattern like from both of them would be different, and hence they would overlap, and which would like affect our study of like crystal. So it becomes essential to like pick one wavelength and eliminate all of them, like absorb all the other X-rays. So for that we use X-ray filters, absorption filters. And the way these absorption filters work is, so first of all, the material is chosen such that, suppose we know that as if we like increase the energy of X-rays, the absorptivity, like the percentage of it absorbed is like decreases, because high energy X-rays are not absorbed as much as the lower energy X-rays. So we have, for instance, as shown in this curve. But if we can choose the target metal such that the frequency of X-rays matches the resonant frequency of the filter. What I mean by that is, suppose at this wavelength near K beta, suppose we chose the filter such that at K beta, the photon is absorbed by the lower energy electron and gets excited to higher energy state. Suppose it matches that frequency. So in that case, the K beta will be absorbed like way more than K alpha. Hence we can separate it out. Like for instance, if we use copper K alpha K beta emissions, and we use nickel as like a filter, the absorptivity of K beta is like 6 times higher than K alpha. Hence we can obtain only the K alpha radiation and do our experiment properly. We also have another diagram here, so like this is more clear. So as we can see, the absorptivity decreases, it suddenly increases at this point, and then it decreases again. So the K beta is filtered out and only K alpha remains, and it is shown here. So for copper K alpha, the intensity is much higher than K beta, as we can see here. Now what are synchrotrons? Now for some experiments, like we need extremely high energy X-rays for to perform them. And when we use the hot cathode tube, the ordinary hot cathode tube, what happens is that the intensity is not high enough to produce those experiments. And also sometimes you need different wavelengths of X-rays to perform an experiment, like a bunch of X-rays for perform experiment, like have high like range of X-rays to be produced. So for that we use what's called synchrotrons. So they are kind of like particle accelerators. So what happens is using different sort of magnets, what happens is the electrons are accelerated, and yeah, they are like sort of they move around in a circle, they are accelerated, and their kinetic energy also is increased using magnets. So when their energy becomes high enough and they are strike the metal surface, extremely like high intensity X-rays are produced, and a huge, like a very broad spectrum of X-rays is produced. As we can see from this fact, that radiations from synchrotrons are like up to 1 billion times more intense than the ones from hot cathode tube. So yes, synchrotrons are very essential tool for can be used for like certain experiments. And yeah, so here is a photo of a synchrotron from Argon Astral Laboratory, and yeah, this is the end of part C and also the end of assignment. And yeah, thank you so much for giving me this opportunity.